Hello and thank you for joining me. I'm Dylan Valerio, and this video is about my latest joint competition in Kaggle, the SIIM-ISIC Melanoma Classification Challenge. To help me understand melanoma, I've asked the help of my doctor friends to give me references, and I will share them to you as well as my solution later. This is not intended as clinical advice, so if you feel or see anything abnormal in your skin, please consult your dermatologist. In this competition, we are tasked to identify melanoma. Melanoma is a kind of skin cancer, which is the most prevalent type of cancer in the United States, and melanoma alone accounts for 75% of cancer deaths. Now, this competition is from the Society for Imaging Informatics in Medicine and the International Skin Imaging Collaboration. Now, the objective of the hosts here, and it was also my hope that we can develop a detector for early stage melanoma, specifically distinguishing from benign images from the melanoma images to better support our clinical dermatologists. Melanoma arises from the malignant transformation of melanocytes at the junction of the dermis and the epidermis. Now, similar to other types of cancer, there are several stages. Stage 0, otherwise known as in situ, it's where the melanoma cells are found only in the outer layer of the skin. For stage 1, the primary melanoma site is still only in the outer layers of the skin, the epidermis, and it's still very thin, less than 2 millimeters thick. For stage 2, the melanoma site is thicker than stage 1. It's extending further into the epidermis and reaching into the dermis. There might be some ulceration or some raised sites in the initial area of the melanoma. For stage 3, and there's actually many stages in between stage 3, it describes melanoma that has spread locally, like it has given birth to new satellite tumors in the skin, and it may be spreading into nearby lymph nodes, 2 or 3 lymph nodes, but it's still relatively local in the site. For stage 4, this stage describes melanoma that has spread through the bloodstream to other parts of the body. So if one may have a melanoma site already in one part of the arm, and then the bloodstream may extend it to the other part or to the other limb. To identify melanoma, well, for a very definitive diagnosis, an actual biopsy is needed, where the clinical dermatologists take a sample of the skin. Although there has been this method called the ABCDEs of detecting the illness, and it's an acronym around asymmetry, border, color, diameter, or if it's evolving. And this is a simple chart that tells us whether if there is symmetry or relative symmetry, then the lesion is benign, whereas if it's not in symmetry, then perhaps it's a sign of early stage melanoma. Border is also another factor, as well as multiple colors. Also, for the diameter, if it's small, then maybe it's just your typical mole. But if it's rather large, then it may be a sign, again, of early stage melanoma. If it's evolving, if it's on a month or week to week or month basis, it's changing in size, shape, and color, then that may also be a sign of early melanoma. Now, in a study done by Klein, Wessling et al., they've tested or they've gathered literature around the accuracy of this method, and we find that, well, it's very sensitive, meaning that if this type of test considers you as early stage melanoma, then it's very sensitive, but it doesn't cover a lot, right? Its specificity leaves a lot to be desired. Therefore, it may leave false negatives, giving us a false sense of security. So really, a biopsy is needed. The dataset also contains metadata around the samples. And one of these metadata is about age. And I share here the histogram of the ages in the sample, as well as the percentage of benign and malignant sample in the specific bin. Now for the left side, these are the raw counts histogram, and it may be quite hard to see the differences per bin. So I give to you also the normalized histogram on the right side, where you see 100% stacked bar chart. And now this will be very obvious to see that for ages above 60 or even 50, there are more percentage of malignant lesions in these samples. The competition hosts have shared high-resolution images amounting to 100 gigs worth of data. These are either TF records, DICOM, which is the industry standard for medical imaging, and your good old JPEG files. The samples amount to 33,000 training images and 11,000 test images. On the right side, you are seeing benign lesions or moles or nevus from all over the body. You'll also see a lot of hair in some of the images, and then for some of the images, you will also see some ruler or measurement type uh, pigments in the image. Now, the computation has also shared a lot of benign images, and turns out that these are also signs of other skin conditions. So we have seborrheic keratosis, which are small and barely elevated papules that's kind of warty sometimes. You also see here lichenoid keratosis, which are solitary. They can be quite dusky red, and they may be raised. And these typically need to be biopsied since it looks very much like basal cell carcinoma, another type of skin cancer condition. Lentigos are pigments that are flat or could be raised slightly, and they are darker than most freckles, but unlike freckles, they don't fade over time. You also see here in the dataset some solar lentigos, which are also called liver spots, which are caused by extended exposure to UV radiation. The computation also shares melanoma images from different parts of the body. So we have images here from the torso area. These may be quite large, larger than their benign counterparts. We also have images on the head or neck, and some of these images bear some markers from the dermatologists. The lower extremities, which are the lower limbs, and the upper extremities, which are your upper limbs. Before the rise of deep learning, traditional feature engineering in computer vision is done with a lot of image processing to help the researcher elevate the sites of interest. So for example, on the left side, if you have the original image, you can employ techniques to reduce noise in the image. Then you can employ different versions of Gaussian blur or blur. And then you can also adjust the contrast of the image so that only the particular sites of your interest would pop up. Then from there, you can also apply more advanced techniques like Otsu's thresholding, where it simply put, it gets the most contrasted parts of the image. You can also get orb features or other types of feature descriptors in your image. So orb features is a type of point descriptors that capture little sites in your images or your patches of your images that bear some characteristics that would describe that particular image. Now, come deep learning in computer vision, you can imagine that the deep learning network already does all kinds of pre-processing steps that we've seen in traditional feature engineering. They will discover these filters and point descriptors all in one go. So that means all your basic filters, all the way up to your advanced filters, and combinations of the basic and advanced filters with hierarchies already built in. In your deep neural networks, you will see, for example, in your shallower part of the network, you can discover here on the image some filters that are capturing really basic types of features like lines or particular shades in your images. And the deeper you go, the more complex the features that you will discover in the filters that you will see in your deep learning network, like stripes or dots. And then further on, you will see some motifs or themes already forming. And then in the deepest parts of the network, which is the combination of a lot of these features, you will discover very complex patterns that it's trying to extract. This describes my modeling pipeline, where we first begin with our data pre-processing. We first resize our images to 256 by 256. And for our metadata features, we've just used one hot encoding. To increase the size of our dataset that is required by deep learning methods, we do simple augmentations, we do crops, we do random flips, horizontal and vertical. We also randomly adjust our brightness, saturation, and contrast of the images. We also do advanced augmentation, such as cutout, that is randomly blacking out some parts of the images so that the model isn't biased to the superficial parts or any hyper-specific parts of the image. We also add random hairs because sometimes, and actually most of the time, the images could contain a lot of human hairs, and therefore we want the model to not be biased against those hairs. For the specific deep learning method, we've used EfficientNet, pre-trained on ImageNet. EfficientNet is quite efficient, as its name suggests, in that you can adjust its input resolution, width, and height to better suit your computational resources on hand. We've also used 5-fold training. That means 5 EfficientNet models trained on different cuts of the dataset, and we average those predictions. We also do test time augmentation. That is several augmentations of the same test image is averaged together so that we can achieve a sort of different looks in the same image so that we can get a better prediction. We've also used learning rate reduction on plateaus in the loss function, as well as the ADAM optimization method of optimizing our parameters. This is the type of domain-specific augmentation that I personally is very excited about. So we have seen a lot of hairs in the dataset. So to prevent any bias towards these hairs and also to effectively increase the size of our dataset, we have employed a random hair augmentation technique where we just add randomly numbers of hairs from the original image to the augmented image. With our methodology, we have achieved the following metrics. For my method, we have achieved 0.897 AUC on the public test set. Now for the following, we have set the threshold at 0.1 to maximize specificity. So we have 0.9 negative predictive value and 0.29 for the positive, that is the malignant class. Specificity, or the percentage of healthy people that are correctly identified as such, which is 0.85. Sensitivity for the malignant class, that's 0.4. So for this one, we have compared it with the ABCDE method that I've explained a while ago. And so far, we only have specificity and sensitivity metrics. And we can see here that we have achieved a higher specificity as compared to the ABCDE method, which means we could have a good baseline model for a presumptive test. That is a method that says that, hey, you're healthy, and therefore you have a high chance of not having the disease. But take note that the sensitivity is quite low, meaning for the malignant class, it may not explain the reason why you have such lesions. So you should still have the biopsy to really have the definitive diagnosis. This test could only be presumptive or a screening test. A deep learning model is quite difficult to interpret, and there are a number of methods to see what the model sees. So this is what the model sees on a true positive. We've used a technique called salience maps, where we measure the gradient with respect to the label and the input image. And we notice, or we try to track how a small change in the input pixels affects that specific prediction. So we have here on the left side the input image. And here you see for the lighter colors, that's where the model focuses its attention. Or quite technically, that's where the gradient observes a lot of difference if we change those areas. So the model here, we can see it's focusing on the lesion area, the one here in the middle of all the hairs. And notice that it's not focusing too much on the hairs in the middle. But we can also note that it looks at darker pigments over the corners. Now, it's not as straightforward, really. So we have some focus areas that are not on the areas of interest. So for example, for a particular image, TP-1, you can see that its focus is quite on the middle, but not on the entire lesion. For TP9, it's also matching quite, but take note of TP8, where the focus is quite spread out. The same is true for saliency 10, which focuses on like the entire image. This is what the model sees on the error cases. This is the false negatives, or the cases that he has failed to detect. So for these samples, the focus areas are quite uniform. I see here that it's not really seeing a lot of focus on the areas of interest, that is our lesion areas for the malignant tumors. And that is why perhaps the model has failed to detect these images. These images are false positives, so some hotspots are focused incorrectly. Notice still that the model ignores the hairs, so that perhaps is an achievement on the model's part, that he has learned to ignore these lines throughout the image. As you can see here, this is a false positive. This is quite a low, small mole for FP1, and the saliency map is focusing just on that small area. And we see as well for FP3, this is not a malignant tumor, although it quite looks like it because there is no asymmetry, or there is no symmetry, and there seems to be a dark pigmented area over here. Currently, I am at the 984th place, which is AUC 897 out of 1,681 participants or teams. That's a long way from the finish line, but I think I've achieved and learned so much in this competition, specifically the domain-specific augmentations, as well as the architecture of the efficient net and how to incorporate the metadata information as well. For further work, I'd like to work with higher resolution input images. If you remember, we're only using 256, but really some of the images are very large, like 1,000, more than 1,000 resolution. Of course, we'd like to experiment as well with deeper and more regularized architectures. Efficient net is, as they say, it's efficient, but that is in terms of computational power. So I haven't yet tried deeper ResNets, for example, or other types of architectures, or even GANs to do the pre-training perhaps, and to get the optimized parameters specific for this problem. But as it is, this is the way it goes, and I'm very happy with the results. It's a good presumptive test for now, and I hope that in the future, truly we could have a good predictive model just from the images of the lesions, so that we can have a good screening test for our for early signs of melanoma, to also help out the community and also to screen for the work of clinical dermatologists. With that, thank you and see you in the next video.